Hello once again. By the end of this video, you should be able to write mathematical models for exponential scenarios. Basically what that means is you should be able to apply exponential models to some different scenarios or word problems. So the whole topic of today is exponential growth and exponential decay. So let's break down what those mean. So we've been studying exponential and log functions. So let's just say you have an exponential function that's m of x equals a to the x, where a is some base and your input in the function is x. So what happens to your function if your growth rate is a positive integer, 1, 0, or a fraction or decimal? Now when I say growth rate, I just mean the base of your exponent. So if I have a function that's like 3 to the x, my growth rate is 3. If I have 10 to the x, my growth rate is 10. Now the reason that's called your growth rate is because that's what you're multiplying repeated amount of times. So that's like the factor by which your graph will be growing. So we're going to see what our graph looks like for a positive integer, 1, 0, a fraction or decimal, and I suppose we should also throw in a negative integer. And in order to do this, we're going to take a look at Desmos and kind of also look at if we evaluate the function for these different things, just kind of using our brains. So I'm going to open up Desmos. I have the graph y equals a to the x, and I've added a slider for a, so I can change the value to be whatever I want it to be. So right now a is 0. So if you have 0 to any power, almost any power, the output's always going to be 0. Okay, the only time it won't be 0 is what if you had like 0 to the negative something. Because if you have 0 to the negative something, the 0 is going to go to the denominator and be 1 over 0 to that power. And you can't divide by 0. So none of that will work. So that's why when you look at Desmos, my graph, well, the outputs are all 0 for any x value. All my y values are 0, except that graph doesn't go towards the negative direction at all. Now, if you think about the base as a growth rate, this makes sense. There's no growth. There's 0 growth. So your graph never, quote unquote, grows. So you can write next to the 0 that there's 0 growth. Or you can say it like flat lines, if we're being super precise. Okay, write whatever notes to yourself that you would like to include. Okay, let's change this up, and let's just say you have any positive integer. So positive integer would be like, I don't know, 6. So if you have a growth rate of 6, your graph will look something like, if I could zoom out, your graph will look something like this. Okay, it starts growing pretty rapidly. Whereas if you have a growth factor of 2, well, it's still going to kind of grow as you read it like a book from left to right, but it's going to grow a little bit slower. And then a growth rate of 10 would grow even faster than the growth rate of 6. Okay, it gets steeper, faster. So as your growth rate gets bigger in the positive integer, it's going to grow more quickly, which makes sense because your growth factor is larger. But all of these are going to start off small and get big. So a positive integer is really going to grow. It's going to go faster as your base is larger. Okay. Whereas a growth rate of 1, it's kind of similar because that's a positive integer. But if you have 1 to any power, the output's always 1, no matter if it's positive or negative. So again, if you're thinking about this as a growing factor, if you multiply something by 1, there is no growth, there is no change, because that's the identity of multiplication. 1 times anything is itself. So again, 1 is also no growth. Okay, so 1 times anything is not going to change it, so there's no growth. And I suppose you should just note the difference between these two is you can't have 0 to a negative exponent, but you can have 1 to a negative exponent. Okay, let's try a negative integer before we do fractions or decimals. Okay, so if I make my a negative value, you don't see any graph. And I wasn't going to talk about this at first, and I just kind of added it in because this is an interesting thought. So if it's a negative integer, and I made a table, so like negative 2 to the x, well, what would happen if your x was, say, 1/2? Then you'd be taking the square root of negative 2, because negative 2 to the 1/2 is the same as taking the square root. and that's imaginary. So when we talk about exponential functions, we always restrict our base to be a positive number or 1 or 0 because we don't want any imaginary outputs. So that's all I'm going to kind of say about negative bases. So by this I'm just going to say don't do it. No, you can't. We'll get imaginary stuff if I put in certain inputs. Now I know not every input is imaginary, but because some of them are, we don't do negative bases. Okay, last example is a fraction or decimal. So going back to Desmos, I've restricted our a values to just be from 0 to 2 because we know negative numbers don't give us a function. So we're going to look at what happens when it's a fraction. So something like 0.25 or 0.5, what do you notice compared to what we saw before? And the answer is these graphs reflect over the y-axis. And the reason that is because if you multiply 1/2 an increasing amount of times, it's going to get smaller. Just be careful to note if you're talking about decimals, we're talking about decimals between 0 and 1. Because if I have like 1.5, that's still going to grow. Because if you multiply 1.5 an increasing amount of times, it is going to get bigger. So I should say a fraction between 0 and 1 is going to really shrink. Okay, so a number would grow. If you multiply 3 a bunch of times, that grows. But if you multiply like 1/2 by 1/2 by 1/2, that's going to get smaller and smaller and smaller. So that's why it looks like this. Whereas our positive integers look like this. And these are really the two cases we're going to focus on. One is a growing factor, one is a shrinking factor. And one of them is exponential growth, and one of them is exponential decay. I hope you can guess which one's which. So exponential growth is when your graph is growing. So as your x values get bigger and bigger, your y values get bigger and bigger. Whereas decay is as your x values get bigger, your y values get smaller. So your graph is growing or it's shrinking. The formulas for exponential growth and decay are as follows. These should look somewhat familiar because we talked about compounding interest continuously. So when we're talking about exponential growth and exponential decay, we're talking about growing or decaying continuously. That's how we define this E. So this formula should look like our interest formula, A equals P e to the RT, which is basically the growth formula. Now, in other contexts, some people say P sub 0. That's the same thing as this P here. That P sub 0 is just your initial amount. Some people write P sub 0 because like 0 meaning initial, so it's like what you start with after no time, 0 time. And instead of having an R and a T, some people write it as KT. And I'm showing you both because I believe this is what your book says. But K is really just your R, which is your rate. And T is the same. T is time. Decay is exactly the same, except it's negative KT. So why does that make sense? Well, if you have like 3e to the negative 2t, that negative exponent would make this a fraction. And if this becomes a fraction, then you really have exponential decay. For a little bit of a further explanation, let's say you plugged in, well, I don't even need to plug anything in. If I simplified this, this would be 3 over e to the 2t. And as t got bigger, this fraction would get smaller and smaller and smaller. So as your t gets bigger, your graph gets smaller and smaller and smaller. That's why this would be decay. Okay, so they're the same formula, except one has a negative sign to make it decay, to make it become that fraction and make it a shrinking factor. Initial amount, E represents continuous growth, K is your rate, T is your time. Let's jump to some examples. Okay, so first you always want to identify, are you looking at exponential growth or decay? So let's look at one example and determine that. So each year, the local country club sponsors a tennis tournament. Plays start with 128 participants. During each round, half the players are eliminated. How many players remain after 5 rounds? Okay, so each round, half the players are eliminated. So you start with 128, but then they get eliminated, and eventually there would only be like one at the end, one champion. So this is an example of a graph that would look like this. You start off with a lot, and then it gets smaller and smaller and smaller. So this would be exponential decay. So if it's exponential decay, you'd want to write your exponential decay formula. Reviewing that, it's decay of t, but you can call it whatever you want. So I can call it like, I was going to say t of t. Is that confusing? I don't know, but I'm thinking tennis of t equals your initial amount, okay, e to the negative kt. If you don't like that, you can also say just p e to the negative rt. So it's like negative per versus positive per. I don't know, whatever works for you. You might see both forms, so you should be familiar with both. I'm not actually going to solve this problem. I just wanted to use that to talk about the thought process or the beginnings of it. So first, decide if it's exponential growth or decay, then write down the formula, and then we'll plug into the formula. So let's try another one where we actually finish the problem. So you've inherited land that was purchased for $30,000 in 1960. The value of the land increased by approximately 5% per year. So what is the approximate value of land in 2011? So it says that the value has increased. So over time, you start off, not small, but you start off smaller, and then it grows and grows and grows. So this is an example of exponential growth this time. So then you want to write your growth formula. So we're talking about land. So I'll do land over time, and that's my PERT formula. So it's initial e to the rate times time. No negative because it's not exponential decay, it's growth. So now we're going to plug in what we know. So P is my initial amount, which you started, or I guess the value of the land was $30,000 because that's what you purchased for it. So that's where it began, $30,000. Okay. Now we know our rate is 5%, but I want to write that as a decimal, so 0.05. And our time we actually have to calculate. So how many years is our time? So how many years are there between 2011 and 1960? Okay, the answer is 51. Now this is something you could just plug into your calculator and figure out what the approximate value would be. So in theory, it should be bigger at the end because it was growing. That's a good way to check your work. If it gets smaller, you probably did something wrong. Or not probably, definitely. In terms of how you plug in this calculator, my recommendation, if you don't have a new calculator, would be first to plug in e raised to this exponent. Hit enter and then multiply it by 30,000. Sometimes you tell your calculator to do the order of operations for you. It makes the calculations a little bit easier. Otherwise, just make sure you use parentheses or put stuff in the right place. Okay, so you can get the output on your own with your own calculator. Okay, and there's a couple of different examples here for you to try. I do want to say in these word problems, I'm just showing you examples of like how you'd plug in and what the formulas actually mean. Now, obviously, you've learned how to solve logs and exponentials and all that stuff. That probably will come into play at some point during our exponential growth and decay conversations. Okay, but that's all I have for you in this video today, so please come with questions. Have a great night.